Hey, John here. Let's look at Chapter 4 of RVAL-P. We've seen this document many times in this playlist of lectures. This document includes kind of like a how to get started in here, but we got to mix together a bunch of things. Like how do you even run the compiler? Where is the compiler? How do you get one if you don't have one? All these mechanics are usually harder to deal with, in my opinion, than it is to actually just write a stinking program to begin with. So let's kind of go over that in one fell swoop so that everybody knows how to get this thing to just compile. It's easy to write a program, especially with one single instruction in it, which is what we talk about right here in this document. Let's write a one instruction program that simply says e-break, all right? Run this program, please. Instruction number 1, halt and stop. Let's see if we can get that to run, okay? How do we build such a thing? You read in here, I talk a little bit about this thing, and I talk a little bit about a simulator called RVDDT, which I have the source code to in my GitHub page. If you're one of my students at Northern Illinois University's Comp Sci 463, don't get a bunch of things in your head that you're going to go be able to grab the homework assignment off of that simulator because it is written radically different to what I assign in class. On the other hand, if you're following along at home, you're not in the class, you want to play around with this stuff, you can go ahead and get the RVDDT simulator. And that is I wrote this simulator, by the way, solely to generate these diagrams in this set of notes that I'm putting together called RISC-V Assembly Language Programming. You'll notice all these fix-me's over here. I'm so sorry. Look, it takes forever to write these things. This is the minimum set that I can, my lecture notes right now that I've put together here. It's these some of these sections are really for myself more than for the general public so that I can just get through a lecture. If you want to contribute or you've got opinions on what's good, bad, and ugly, feel free to throw in any critical comments or even contributions on GitHub or the comments below in this video on YouTube. More than happy to take them and take them into account and maybe improve this for everybody else down the road. If you're really up for punishment, feel free to go over to GitHub. In the preface of this document, I talk about the GitHub links and stuff, and they'll be in the description below this video online. Anyway, if you really want to take a tear into LaTeX, if you don't already know it, this is probably not something you want to just dive into. I'm more than happy to grab this way. These numbers are over here. You want to change a paragraph or something, or put in a suggestion, refer to these numbers here and the version of the document in case you got an older one or something like that. Put this tag in there as well. This is the GitHub version tag for this particular version of the document you're looking at right now, and these line numbers are tied to that. Okay, again, a tangent there, sorry about that. But if you want to knock yourself out, the short of that digression is LaTeX is not something you can learn on a Saturday afternoon. It's just not going to happen. So again, if you want to contribute, don't worry about it. I'll write that crud for us. Just email me or send a note in the comments section. Anyway, okay, so what's going on here? We all know how e-break already works. Anyway, we wrote a simulator. What this thing does is tell the simulator to stop running and terminate thyself, okay? And I give you the encoding of what the e-break instruction is supposed to look like there. Here's the entire source code of a program that has one single instruction in it that says e-break. Let's figure out how to compile this thing and run it, okay? Again, if you're at home, you want to use RVDDT, you run it exactly like this, and you'll see what happens. If you're running it on the simulator that we wrote in Comp Sci 463, we got a little bit different situation. Okay, so here's these files. Here's ebreak.s, and I created a Makefile. This is on Hopper at Northern Illinois University. So any student who wants to can go in here and steal these files as a convenience. I'll also put them on the course website, but it's easier to just say recursive copy on Hopper than it will be to download them from the web and then copy them over to Hopper, or use wget or whatever, however you want to do it. They're already over here, and you can just reach in here and steal them out of my home directory right here. This is where I'm at, okay? I give you full access to this stuff. Let's look and see how we compile this. This is the entire point of this video. How the heck do you get these things to compile? What do you do? This is kind of hard to read like this. Let's just open it up with Vi and see what's going on here. Okay, For the environment on Turing and Hopper, I hard-coded these paths in here. The easiest way to do this. All right, I apologize to those of you elsewhere. You're going to have to change these to wherever it is that you've installed the compiler and stuff like that. If you want to build in your own compiler and stuff like that, that is available. The details on how to do that is in this RVAL-P document from my GitHub site, and it's in an appendix somewhere here. Installing a RISC-V toolchain. These are the exact commands. They're also on the website for this book as well as for RVDDT on how to do this. These notes I tested on Ubuntu 18.04. The system that this is recording on in this screen is Ubuntu 20.04, and Hopper and Turing are running a very modern version of not Raspbian, Debian. I'm sorry, it's the same OS that's on a Raspberry Pi. Anyway, the Debian image on Hopper and Turing, as well as Ubuntu, all work, and this is fine and dandy. I guess I last tested these exact notes in June 9 on my box when I wrote this thing here. I've also built it, is my point, just a few months ago, because this is a brand new system. It's an AMD box that I got this summer. I could probably update these notes and the various dates and say, oh, now it works on a more modern one. But my point is, it works on enough that I'm pretty sure these are very stable and correct commands. These are exactly what I typed in here. If you're smarter than me, knock yourself out. But in the end, be it known that when I configure and I run this compiler, this is exactly the configuration that I use. This is the number one most important thing when it comes to the notes on why my compiler will do what it does. Okay? If you compile something else, you're on your own. Don't tell me you're missing a bunch of libraries because you compiled an RV64i and nothing works anymore. All right? Full disclosure, this is how I built everything. Okay? When your system fails, if you didn't use these instructions, try it one last time the way I say to do it before you complain. That's all I'm saying here. All right? That is what was installed right here. This right here is the install directory on this particular machine, on Turing and Hopper, where the compiler tools were told to be installed using the technique in RVAL-P that I just went over. Okay, so it builds this whole tree full of files, and one of them is the binaries directory where all the executables go. Now, I also, on Turing and Hopper, have the binary executable of my solution to assignment number 5 stored in this file right here. So you can run mine if yours doesn't work, okay? This is not, this is a kind of a cumulative assignment sequence. For those of you in the class, you already know this. If you're watching along at home, you may not realize that. This is my solution. I don't give you the source code. I give you the executable here, all right? What's going on here? So in all Makefiles, the first rule that is encountered is the default rule. And by convention, everybody seems to call that all. And be it far from me to fray too far from convention, right? What do? I want to create a thing called ebreak.bin, and I want to create a thing called ebreak.list. Okay? And here are the rules. Create ebreak.bin from a thing called ebreak. Do this command. Create ebreak.list from ebreak and do that command. All right? So let's first look at how we create this ebreak thing. Ebreak is an executable program that's compiled from ebreak.S. And anything that ends in a .s on Unix, Linux systems are assembly language source code files, okay? The capital S to the GNU compiler means that this file should first be run through the preprocessor just like as if it were a C program. In other words, I can put #include in there, I can put #define in there, and things like that, okay? If I put a little s after it, it will not run it through the preprocessor, okay? I write all my assembly language programs with big S, whether I need them or not, just because of habit, okay? So what's going to happen, I'm actually going to run the C compiler on this. As the C compiler recognizes, if you look at it, how the C compiler works, it really compiles the C program into assembly language, then it compiles the assembly language into binary. So it already knows what this thing is. It's part of what it knows how to do anyway, all right? So it may seem odd that I'm running GCC, and those of you that know advanced tools, I don't run it with GAS directly, because GAS is not going to, I don't think GAS knows how to run the preprocessor. So I just run the GCC command on these things, all right? So let's look and see what's up with all these options, right? So the only difference between this and what you're used to seeing, you compile a C program, you might just say compile, something .c or something .cpp if it's, C++, and -o, and here, put the executable in this file over here. That's what you'd normally do. Now, I've simply added a bunch of options to this compiler. What have I done? Well, some of this you should recognize right away. Look, when you compile this, compile it to run on an RV32i machine. Okay? Use this application binary interface specification, the ILP32. This has to do with how the compilers run. There's other ABIs and things like that. So this combined represents the formal if you may, definition of what it means to create an RV32i program that runs the way I've been speaking of in my RVLP document in lectures in class. Okay, so this is compile it so that we recognize the output. What else is going on here? No standard library means do not help me in any way, shape, or form. Actually, this combined with that means this, okay? The no standard lib essentially means don't go out and look for things like string copy and stuff like that. Use and incorporate no subroutine libraries whatsoever. So I'm not surprised by something all of a sudden showing up in my code. That's why I put that in there, okay? What does this thing do? Well, that could be a lecture in itself. The short of it is, this tells the compiler that there is no operating system when this program runs. We're running it on a simulator. Do I have Linux loaded in there? No, I don't. Do I have some other? No. So this is even more brute force. Don't help me. Don't assume anything. Then just don't include the standard libraries, okay? So this is saying, don't even think I have an operating system. In other words, I can't read and write and print things. And there is no keyboard. There's nothing, okay? Absolutely nothing. That's what this thing really boils down to. Now, if you want to know more specifics about what freestanding really means, what you want to do is find your way over to this website. This is www.openstandardorg. Do a Google search on this thing, okay? This is the formal specification of the C language today, the latest official release, right? IO/IEC 9899:2011. That is the name of a document that is a formal release of the technical specifications of what happens in a C program. Now, I'm going on this diversion a little bit to make sure everyone understands what this website really means and how you get these documents and stuff like that. So what happens is the ISO committee that meets and discusses this stuff happens a lot over email. And what they do is they write a document and they say, here's all the rules of how C should work. Okay, we're on C11 right now, apparently. Before that was C99, okay? It's probably the 98, 99, 2011. This combined thing probably, I don't know if it really is, it probably means that we're really on C99 plus some extra notes that were upgraded in 2011 or something like that. Regardless of what it means, the latest, greatest standard that's official is C11. Now, if you read this sentence right here, the latest publicly available version of the standard is available in a document that is called WG14N1570. I think this means working group number 14 of the ISO something or other committees, okay? And N1570 is just a document that they floated around, most likely via email, to all of their members and posted publicly for comments and reviews to make sure that they got everything just right in that document. That was done on this date right here. Now, notice it says this is a Working Group 14 working paper. However, it does reflect what was to become the official standard at the time of issue. So what we're really looking at is the absolute final public draft that everybody voted was okay. And the only difference between this draft and the official specification is kind of pretty much the fact that it says draft on it before everybody voted. And the official one, simply they remove the draft and then they say, oh, this is the final one. Now, why do we care about all this garbage? Well, if you go over the documents, you're trying to get the official one, you're going to have to pay for it. I don't know what it costs, but it costs money. But they do this as a nice courtesy of pointing out, by the way, the very final draft was this, and it's the same thing, really, okay? So I already clicked on that. It's probably free for me to show bits and pieces of this on my YouTube channel without getting into trouble with rebroadcasting and stuff like that. So what did I do in here? I searched for the word freestanding in this document, and there's like 2 or 3 paragraphs out of 700 pages of excruciating legalese looking narrative about how everything is supposed to work in a C program. And the bottom line is that it says, look, there's 2 ways to run a program. One of the ways is in something called a hosted environment, and the other one is called a freestanding environment. Hosted environments is what you're probably used to from your first C program, your C++, all programs that you've ever written that run on a command line on any operating system, those are all hosted, okay? If you've ever written a program that runs on something like an Arduino or something like that, those are freestanding programs. There's no OS in there. They're a very limited environment, okay? And in fact, you're very limited to the fact that these are the only header files that you can actually count on being present in the environment that you use to compile your program. You want anything beyond this, you got to supply it yourself, in other words. And look at these: float, ISO 646, limits, yada, yada, yada. All these header files really don't have a lot. There's no real serious library functions in here. These are just filled with macros like standard int. What's in there? A bunch of macros that define things like uint64t and uint32 and int64t, so on. These are just simple header files. What's in here? Things like, that's where null is defined, okay? Standard Boolean. Now, in a C program, there are no Booleans. So they just have macros that says, you know, if I wanted to make something and I call it a bool, well, that's just pound defined it to an int or something like that, all right? So that makes it look like you have Boolean functions and Boolean variables and things like that, like a C program. Standard arg, that is the rules for variadic functions. If you don't know what those are, then you don't write them. Don't worry about it. Standard no return.h. This is a handy little thing that has to do with when you write a function that never returns. There's macros in here that tell the compiler, you know, you don't have to put all your activation record crud in there for this function because you're never going to have to save, you're never going to have to recover. This function, in other words, does not return, okay? We don't care so much about that in this set of lectures just yet anyway. I normally don't use this. It wastes memory a little bit, but because we're on a simulator, I don't really care right now. It is just more complexity. Keep it simple, all right? What's in these other ones? Limits. This will have things like, what's the biggest integer you can have stored in a like a uint16 and stuff like that. Standard align has got some macros that says, you know, hey, this variable, when you put it in memory, please put it on at an address that's a multiple of 8. So you can actually, there's ways to do that in here, okay? ISO 646, go ahead and Google it. It has some stuff about what do you do with people that have anemic keyboards and are unfortunate and don't have a curly brace. Oh, try to write a C program without a curly brace, you're in trouble, right? So what's in there is some macros like the word begin and end that you can use in lieu of curlies if you want. Float.h is just like limits.h. It's full of a bunch of things that says what's the biggest floating point number, what does a nan look like, and stuff like that, all right? So again, these are very limited, okay? So the freestanding program, this is kind of a formal definition of what you got. If you continue to search through this document, you see other things. Oh, that hit on the second word right there in that paragraph. And it gives you some other things about what happens in freestanding environments, like, what is it? Up here, it just goes on to say, if it ever exits, if you have a freestanding program in the main returns, that is not defined, okay? Actually, that's right here. That's this paragraph down here. Okay, what this one up here says is normally, you know, there's a specially designated C function that's called, well, that's your main, okay? In a freestanding environment, whatever that function is implementation defined, okay? It may not start at main, in other words. So again, this is very specific about what these freestanding things, what all of C really is. What's this one down here? There's some comments about threading, and this is where we're going, right? Remember, at this point in these lectures, I want to work on how do we write a multi-threaded program and run it on our simulator, okay, on a freestanding environment. And the comment here is that under freestanding, whether or not you have threads is up to the It's implementation defined. And we're going to see the simulator that we're using will provide a way to run multiple threads, okay? That's really about all there is for freestanding stuff. Well, feel free to read about what that is all about. That's beyond the scope of this course. And in here, this is what I was just talking about. What's in standard int.h, what's in float.h, and stuff like that. And this down here is a summary of what we were just looking at. Down here about the environment. What does it mean if the program starts up, terminates, whether or not you got threads, okay? And if we hit next a few more times, I think that wraps around the entire program. Blah, blah, blah. That's what we're just looking at. More than one thread. Again, the summary, we hit it again. I guess it talks a little bit more about the libraries. If it's freestanding, then you don't have any libraries, especially if you say no standard lib. You have literally no libraries. This is just the index, and at this point, we wrap around the file to where we started, okay? So that's the summary of what it means to write freestanding programs when I put this thing on the compiler, all right? So basically, the whole lot of this means I want you to build me a RISC-V program. I don't want you to use any libraries. If I call any subroutines or anything by accident, give me errors. It'll say there is no string copy, there is no C type or anything like that. So remember what a compiler is going to do. If I told it to compile a C program, it would first compile it into assembler, then it would assemble the assembly language program into a .o file, and then it would link the .o file with any libraries that are necessary, which I told them do not grab any libraries at all, so it won't. And then it takes that combined thing, and it'll save it into a load module, an executable file called eBreak, okay? Now, when the linkage editor runs, what I want to tell it to do is say, look, make sure that the text region, remember, we're creating an address space here, and this executable needs to have a text, a data, and a BSS, and a heap, and a stack, and all that. So I'm telling you, when you do this, make sure the text region starts at 0. Because our simulator puts 0 into the program counter and it assumes that that's where the program starts running. So we have to write our program accordingly, and we have to make sure that the link editor puts things where we want it to go. So we're going to put it at address 0. We're going to set that right here. This thing over here has to do with don't optimize things. When the link editor runs on a RISC-V system, the instructions are written in a very specific way that allows the link editor to make intelligent decisions and discover things that it could optimize after the compilation is done. In short, these don't relax means don't remove instructions that are superfluous. Okay, this is for optimizations. I want you, by saying no relax, to leave every instruction that I give you alone. Because if I let the link editor remove them, I'm going to get disoriented. All right, we're not writing top of the line optimized code here. Quite frankly, we just want to get something to work. All right, so I've shut off every helpful thing that will confuse us to death. That's really what's going on here when this thing compiles. That's what all that means, okay? When we're done compiling this program into this executable module called eBreak, we can then use these other tools that are available that come with the compiler, like obj copy. And what this is going to do is it says, take this thing that I got from the compiler that could be executable, all right, and extract just the instructions and the data. That's what this means. And store just that into eBreak.bin. That is how I create the exact image of the memory in binary for our simulator. So when we say, hey, start up a simulator, put this file as it is, byte for byte, right in the beginning of the memory, starting at address 0, and then execute the code. All right? That's not what an executable module looks like that comes out of the compiler. So we have to convert it from that. We'll have a look-see at what's in here in a minute, just to make sure that we understand what's going on. What does this one down here do? obj dump. This one is going to generate, this is a disassembler among other things, okay? So when I say obj dump and I say all this fun stuff, I'm saying, look, I want you to tell me when you disassemble my program, this will kind of look like what we did in our simulator in our disassembler assignments. I want you to show me all the registers using the X notation. So if I have, register X0, it'll say X0, X1, X2. If you leave this off, what it will do is it will use the ABI names. So if you had X10 in there, it would say A0 instead, because that's argument 0. if you use the ABI names. Now, and we saw that in the table in RVAL-P, which is the same as the table in the official specification that talks about the ABI. All right, so I put this in here so everything uses the X notations. And no aliases is in here because sometimes instead of X0, to help you make it more readable, it puts the word zero, Z-E-R-O, in there. Okay, so this makes the output of this disassembler look a lot like the one that we wrote for ourselves in the course. That's why these are in here. Minus DR is what says disassemble this file. And then I want to save that in this file here, okay? So that's all I've really done. A one line to compile it, take the compiled program, make it into a binary so that our simulator doesn't have to figure out how to read what we're going to see is called an ELF load module, okay? And for reference, tell me what the compiler thinks about disassembling the e-brake program, okay? Now down here I also have a rule that says run this program. It makes it convenient so I don't have to type this in every time. I can just say make run, and what it'll do is it'll run the RV32i simulator that I let everyone use, and I pass it an M10 DIRZ on our binary file. Remember, the simulator M minus M is how you specify how much memory should be part of the simulation. By putting a 10 here, a 10 that's a hexadecimal value. I should not call that 10. It could be confusing. So that's 10 in hex, which is 16 bytes in decimal. Why? Because this file, you're going to see, it has only 4 bytes in it. It's got one instruction, all right? And DIRZ means disassemble the entire program, everything in memory, all 16 bytes, before we run the program. The I and the R mean dump the instructions as they are executed. I want to see them in debug output. And the R means before you dump the instructions, dump out all the registers so I can see what the registers are. Then I can see the instruction that is executed as it simulates it. The Z means when you're done running the entire simulation and it halts, regardless of the reason, dump out all the registers one last time and all of the memory in a big hex dump, okay? So let's go ahead and compile up and run this program, all right? So there's just 2 files. Let's say make all. What did it do? Well, there's the freestanding compilation to make the file. There's the OBJ copy to make the binary. And there is the command that says show me the listing of the disassembled source code from the executable, all right? So we can actually see what we started with if we want to, and then we can see where we ended up. Now, in this case, this entire program has 1 instruction in it, okay? So it should come as very little surprise that when we disassemble it, it still will have 1 instruction in it, right? Let's look closely at the source code here. What do these things mean? The first line here, .text. I'll give you a wild guess on that one. What this means is everything that follows until I tell you otherwise, put in the text region of the code that's being generated, okay? So that's the comment over here. Align to is probably unnecessary in this particular case, but the align instruction, everything that starts with a dot is like a directive to the assembler. So I'm saying, look, when you emit data, make sure that the address it goes into is a multiple of 2 to the second power. So align 2, this is the exponent of 2. Align it to a multiple of 2 to the n, right? Where n is this number over here. So 2 squared is 4. I'm saying make sure that you start on an address that's a multiple of 4. And of course it will, because when it starts, it's really starting at 0. But we're going to see this some more later on when we're dealing with programs that are made out of multiple files. So this is kind of superfluous on the very first file that we know will start at address 0, but it is not for any other file that might start, somewhere else in memory. This is very important so that the instructions come out in the right spot. Now, I don't know. I suspect that maybe the assembler will put any real instruction by definition has to be in a multiple of 2 anyway, or rather a multiple of 4 for by default for RISC-V. Anyhow, it might know to just do that anyway. I don't know. So this is, my point is perhaps redundant, but better safe than sorry, okay? What does this thing do? Well, this is, again, a directive to the assembler. It says, when you run into a symbol called start, assume it's global. which means this is, in assembler, this is the same kind of thing as making a global variable in your C program. Like, you're going along, you might say int x, that's not in a function, right? Well, that's a global variable, right? You could also say static int x. This would not be a global variable. This is only available in the file within which it is defined, right? So in assembler, what you do is you say global start. Well, that makes it global. Or otherwise, I could just put start in here and not do this. That would be the same thing as like in a C program saying that you have a static variable that is in a file. So it's accessible within that file only, all right? So that's what all these directives mean. We already know basic assembly language. We know what a label looks like, and we know what the eBreak instruction looks like as well. So that rest of this thing is pretty much intuitive. So this up here is just boilerplate, and this is the point of showing it and beating up this this topic is if you've never used the GNU tools and you've never written a RISC-V program, this is your boilerplate junk that needs to be at the beginning of your assembly language programs. Okay, so now remember, we created this list file with their own disassembler. Now, this one's kind of fancy because, remember, their disassembler reads the load module, not this binary file. Notice the binary file has 4 bytes in it. That's the one instruction, okay? Look at this thing. It's got over 4K in it. It's got 4,680 bytes more than we really wanted. So, newsflash, you don't want to execute this program. You really do want to execute the executable part of the text and the data out of there, which in this case is the one instruction, and execute this with your simulator, all right? Well, you could make a fancier simulator that knows how to read the files of this format, but that would just be more work. This is hard enough to do as it is. It's nice to use that OBJ copy utility program to just do this for us. It makes our lives a lot easier, okay? Anyway, the OBJ dump thingy, when we ask it, please disassemble this file and show me what's inside it. Look what this thing can do. It says, well, first of all, this is an ELF32 little endian RISC-V application, right? Because there's some header information up here that has all that extra information in there. And it also has information about which parts of this file represent the text region, which parts of it represent the data region, which parts of it represent the BSS, and so on. That's all this extra data in there. It's a little bit of like debugging and symbol information. And as you can see, it knows all the symbols that were in the source code when this thing was assembled. Again, more stuff that's in here, right? So it can tell you that, look, there is a symbol that I put at address 0. Well, that's a good clue that it did the right thing when we said text 0. And at address 0, and when it prints out its addresses for its disassembly, it suppresses the leading zeros. Sorry about that, but that's how this one happens to work. There is the executable instruction, the full word for the eBreak, okay? That is how this disassembler works. Now, this is more useful when you're disassembling like a C program. When you're disassembling a program you wrote yourself and you told it no relax and no pick and no nothing else and shut off everything, it's just going to send back out what you sent it. So this is a trivial example, but it is the minimum example. So hopefully this is a little bit of an insight as to how these tools work in the simplest possible case. So let's look now at what's in this file, okay? Hex dump minus big C is a great way to get a nice hex dump in a suitable, insane manner where you got all the bytes one at a time over here, and inside the pipes over here, it'll show you the ASCII data that this stuff represents to make it easier for you to find strings if there happen to be any in this file, okay? So hex dump minus big C is our friend. It makes perfect sense that eBreak.bin is 73001000 in that exact order because remember, when we fetch these full words out of memory, they're in little endian order. So look and see what happens in our source code, 01100073 is the big endian, right? So this 0 is right here, and the 10 is right here, and the 0 right there is over there. Makes perfect sense. Now, just for fun, let's look at what's in this load module that we never really talk much about. There's a lot of junk in here. So the first thing that leaps out at me is the word elf right here. Now, this up here is what we call a magic number of the file. And Unix has a lot of this stuff going on, and a lot of it's binary files. It just stores some number up here that says, look, this is a file of type X, so that, you know, anybody using it can kind of figure out what it's supposed to be for. Now, notice this is in very deep and stark contrast to the philosophy behind other operating systems like Windows and Mac OS 10 or wherever that number. Maybe they moved on. I don't know. I'm not a Mac person, nor am I a Windows person for that matter. But those operating systems make a very unfortunate use of assigning great meaning to the names of files. Okay, now Unix does ascribe meaning to files based on their name by convention only, not at the operating system level. And every tool everywhere in the OS is not welded to this notion that the file name extension like .s or .text or .list actually mean anything at all. It means nothing in Unix, okay? It means everything as far as I can tell in other OSs at times. Under the hood, by the way, Mac OS 10 is Unix-based, so while the GUI might present them in a certain way, the OS still works exactly like I'm showing you right here. Nice, whatever, side note. Anyway, in Unix at any time, in fact, you can even use this file command. Let's just run it on every single file. Look what happens in here. It looks inside here, and it says, oh, that's a Makefile, and it's filled with ASCII text. E-break. How did it know all this? That's because of this magic number right here, not because of its name, all right? Which you can clearly see it has no extension, like exe or whatever you might see on some other operating system. It actually opens it up, looks inside the file, takes a peek around and goes, oh, this smells like one of these things, okay? And that's that magic number at the head of the file. Now, this one is a little bit more based on the name of the file, as is the Makefile. It ends in a .s, so it says, well, you know, it ends in a .s, therefore it's probably assembly language source code. And then opens it up, looks at all the bytes, and it can see that it's only filled with ASCII text, so it tells me that. It has no clue what this is. It's just full of junk. I don't know. That's a data file. Can't say anything about it. eBreak.list, I don't really know what I just stuck that, I just made up that name for that file myself. So it doesn't know anything about that by name, so it can't help you out by heuristically playing and pretending it's Windows or anything like that. And it's just, well, it's filled up with ASCII text, and that's all I can tell you about that file. But the real key is this guy here. Anytime there's a binary file in a Unix system, it's going to have some sort of a magic thing at the beginning. These are literally called magic numbers in the context of Unix that is used to identify what it is. Okay, anyway, that's what that's all about. And usually there's even a printable thing in here to help you when you look in the ASCII side, which is why this is so useful. Okay, so what's going on in here? If you look closely, there's a bunch of junk up here that's a big header. Looky here. This is the executable instruction. So hiding in here, it should make perfect sense that this is supposed to be an executable program. It has extra stuff, but buried in here should be the instructions we're looking for. Okay, so rather than playing games with all this stuff, and you can kind of see this starts at this address 1000. Well, if you look around up here, there's a 1000 stored in little endian order. There's also a 4 stored up here in the header. I'm not saying that's what these two things are, because there's a 4 over here as well, but most likely in the header somewhere, it will have a value that says at this byte address in this file is where the stuff, you know, the executable instructions are located. And oh, by the way, 4 bytes of this stuff is the text region and stuff like that. Okay, so if we really wanted to, we could probably open this up, interpret the header, find the instruction details in here, load those into our machine, which would be arguably kind of cool. But on the other hand, if you've never loaded one of these ELF, which is an acronym that stands for executable linkable format, okay? The fact that it is linkable means that this is not necessarily done yet. It's not fully baked. There could be references to addresses and things in here that are not entirely, resolved, as we say. They may not be the final version that you can just execute, okay? That's why we use the obj dump to say, I don't care, I don't want to know about the details of this file, just give me the instructions, and if it needs to be adjusted in some way, or some patches need to, I don't care, just make all that happen and give me the binary image, okay? So this simplifies our life lives greatly not having to poke around in here. But why am I going on about this? Looky what's down here. What the heck is all of this? Now, it turns out that amongst the almost ready to execute code that's up here, there's something called a symbol table in here. And there's various values up here. And then there's this thing called a string table down here. And you can see global pointer, sData begin, BSS. Look, we know what this is, data, and okay, what's that all about? Well, rather than guessing our way through the ELF file, we'll use another utility, nm. It says, show me the names of all the symbols in this load module. And what does this program do but open up this file, sniff around, oh, it looks like an ELF file, look at all this crud in here, and says, okay, here's the names of all the symbols in this program, and I'll tell you where they're supposed to be in the final binary executable image. So this is super useful, all right? And we're gonna make a lot of use of this in the next lecture or two, all right? Now, notice they're in some random screwy order that I find annoying personally. But again, Unix has all these nice and simple, handy little tools. I don't have to write a program. I don't have to have a massive GUI of a bunch of junk that shows me what I want in the order that I want it. I just pipe it into sort because they put leading zeros in here. It doesn't matter. Treat the whole line as an alphanumeric constant value and just sort it accordingly. The little numbers come first. The big numbers come later. Even though it's going to be in hex, it'll still work fine. If all the numbers here are the same, of course, then the sorting will continue to run into the first thing that differentiates anything from anything else, all right? So these over here don't necessarily come in the most useful meaning way because all their values are the same. But let's look and see what's going on in here. Start is at address 0. That should be no shock, okay? What's all this doing in here? What does it really mean? Well, notice there's a thing. First of all, notice every one of these is the exact same address. So the sort function couldn't put them in any great order, a meaningful order. It's just doing it based on sorting in alphabetical. So therefore, it'll tell you about BSS because B comes before D, which is data. All right. Well, look what's happening here. We know about the data region. We know about the BSS. So we've seen stuff about data. What does that mean? Data begin is at 1004. There's another thing called eData, which stands for the end of the data. It starts at 1004. Now, you'll notice because there's the same, that means that there is no data region whatsoever in this program, which makes sense because we didn't put anything in the data region. Notice also that we have this BSS start and BSS end. Now, I don't understand why the convention is to start BSS start lowercase, BSS end uppercase, data begin upper, end of data lower. That is random convention. You can change all this if you want to, but these are the defaults that a lot of people have used over many years. I apologize for the conventions of my elders, okay? That's just the way they are. But the bottom line is we have a way to find out where the data region begins, where the data region, where the ends, where the BSS starts and the BSS ends, and we're going to need that in the next lecture, okay? That's the whole point of this. What's in these files? How does it work? How did it get there? What is it doing, okay? So we're going to compile this into this program here. We're going to throw away the extra crud and extract just the binary image, and just for fun, we disassemble it with using the official tools from the GNU compiler, just like the disassembler that we wrote, okay? That's what's going on in here. Now, look also at my Makefile. I have a little run rule down here, so I don't have to type all that junk in every single time. I can just type make run, and it will run the simulator with the appropriate arguments and stuff like that. For those of you following along at home, didn't go to the course website and look at the assignment that I handed out that discuss how this simulator is supposed to work. This M10 stands for I want a memory that's simulated with this many bytes in it, and this is in hex format. So this is 10 bytes, which is decimal 16. So I want 16 bytes of simulated memory, all right? That's more than enough to execute one instruction. When it goes, I want you to use these other options. The D means disassemble everything before you run anything. If I specify R, I want to see the registers before you execute an instruction every time you simulate one instructions. The I means show me the instruction and disassemble it and tell me what the CPU is doing to execute that instruction, okay? The Z means when I'm done executing the entire simulation and it halts for whatever reason, and the only real reasons this thing ever ends is because you said E-brake to stop it on purpose, or you ran into an unimplemented instruction, okay? Those are the reasons that this simulator will ultimately halt, and use the contents of this, copy this into the memory that is simulated memory before you execute anything, okay? So here we go. It copies the 4 bytes into its memory and then disassembles the whole memory. Should make perfect sense that the 4 bytes that it put in memory are that, and it disassembles it to an E-brake. It also makes sense that this other stuff is simply garbage. Nothing was written in there. For you following along at home, if you look at the assignment that I handed out, the entire simulated memory array is initialized to A5 before we read in the executable binary that overwrites it. You can see down here for a 4-byte file, but in right there. This allows us to kind of get a feel for, nobody ever wrote anything in here. Either the file was never read in, it never put anything in here, or when the program ran, it never stored anything in there, okay? Kind of makes it easy to recognize. It's also a value that is an illegal and unimplemented instruction, so it makes it handy that if you actually branch off into the middle of nowhere, you're going to get illegal stuff, and due to the way this simulator is written, it will cause it to halt right away. It helps it debug your programs. Okay, so what then happens? We print out all the instructions before we execute anything. That's the R. What did I say? Print out all the registers is what I meant to say before you execute any instruction, including the program counter, which is initialized to a 0. If you're eagle eye, you'll notice that there's a weird value in X2. What is that? Well, in this simulator, to make my life easier, what I decided to do is store the value of given on the command line up here, okay? And we round this up to a boundary of 16 for this simulator as well. So if I said, E here instead of 10, it would have rounded it up to a multiple of 16, which would be a 10 in hex, which would be 16 before it ran this. And that value, 10 in hex in that example, would be what's stored in X2, because this thing represents the actual number of bytes in the simulated memory. And we store it in X2 because, as we will see soon enough, X2 is the register that by convention is used for the program call stack, and the program call stack is implemented as a full descending stack. And by putting 10 in here, which points the program, or rather the stack pointer, past the end of memory way over here on what would be the next line if there was another one printed in this dump down here, it allows us, if I said push something into the stack, it would back down, whatever. Let's say I push a register forward into the stack, I would subtract 4 and store it in here. So that's exactly what you want for a full descending stack, as used by the ABI rules for RV32I, okay? So this is a cheap and easy way to cheat and you can find out and initialize that register the way we want it to before running a real program, okay? If you don't have this, which is usually the case, by the way, what you do is you actually hard code in your program a way of setting that when you compile it. You might literally set it to say, I know the memory size will be X, and I'm going to hard code that and stick that in register X2. We're going to see a little bit of that going on as we move forward when we get to writing a multi-threaded program that runs on our simulator, okay? So what do? We dump out all these registers and note the program counter is 0. Then we dump out the entire instruction and we note in a comment over here what it means to the simulator. So at address 0, there's the op code, and there's what the source code looks like, the disassembled source code. And here's the comment over here says, this simulator is going to halt because I got an e-brake, which makes sense because that's what that's supposed to do. Then it says, hey, the execution is terminated by an e-brake instruction. Thank you very much. By the way, I executed one entirely huge whopping instruction before I terminated. And because I said Z on the command line, it dumps out the registers one last time, and none of them have changed. Notice that this simulator doesn't even advance the program counter when it executes an e-break instruction. That may be different on different systems. In this particular system, I chose that an e-break will not advance the program counter. And if you're one of the people that used RVDDT, which you see in the handout here on chapter 4 or something like that. Where is this? Writing programs. Here we go. Remember, this is the program that we're running right here. If you run it in RVDDT and you say trace, what happens is this simulator also does not advance the program counter as a result of the e-break. So if you're really zealous with your typing and you say trace enter, T enter, and you keep doing this manually like I do, the last thing you wanted to do is to move beyond the e-break and start executing garbage down there. So literally, I chose to do this because of how I was interacting with this particular simulator, because I kept on simulating too many things just by building up this rhythm of hitting T enter in doing this. Now, granted, I could have done this, which says trace from address 0 and run 1,000 instructions, or until you hit an e-break. Okay, that I could do as well. But like I said, quite often I'll accidentally just, out of habit, trace something else. Out of habit, just keep tracing due to rhythm after something has ended. So I did that as a favor for myself. So anyway, this is, what do we do? What do we accomplish by this whole thing, right? What's the point? We compiled a program. We wrote a program in assembler. We compiled it. We created a load module. We were able to disassemble the thing. We created a binary executable using the tools on Hopper and Turing at NIU. And you can come in here and grab these files. I'm going to type make clean because this is actually where you're going to grab your files from. And you can run this on yourself. So this is the first of a couple of programs that we're going to write and evolve this into a situation where we can write enough code in assembler to start a C program running. All right, then we don't have to write a ton. I don't want to write my whole life in code in assembler. No. Get out of assembly language as quickly as possible and into a high-level language. Now, you may not like C either, but I can certainly hope, and I'm sure you can appreciate the fact that writing in C is going to be easier than writing in assembler. So let's figure out the minimum necessary stuff that we need to do before starting a C program, all right? And we'll talk about that in the next lecture. Thanks for watching. See you next time.